Hello?
Hello, Ken.
Hello.
Yeah, I was just 5 minutes early. Oh, so we don't have to do this video anymore. But then struck in between that, yeah, maybe you will be attending online. Yeah.
Yes, yeah.
Yeah, we were just talking about this. Yes, I think I should inform you. Apparently, maybe you're already familiar. Apparently, there are vaccination shots being available to those who are not eligible yet in Jackson County, Jackson County Health Department. So just if you're interested, you might want to go and look into their website.
Okay, thank you.
Yeah, they asked me for my date of birth, but they still let me schedule the appointment.
Yeah. So it seems like we are not eligible, but they are not filtering. In fact, they're encouraging the other way. So that's what I have understood. Give me a few minutes, Ken. Set this up.
No, I forgot my pen.
What did you forget? I didn't hear what.
I forgot my pen.
Oh, you mean for the, okay. You earlier said you don't have a pen for paper, and now you don't have a pen for your computer itself. Okay, that can be. Come on. This takes so long. Okay. I need to return this. Yeah. These are the exams. Can you ought to collect it from me later?
Yeah, I can come by later.
And yeah, I think the exams was okay. I was a little picky on the functional derivatives. I think both of you need a little practice on that, but otherwise, I think overall, I think you guys had the idea. but the details were missing.
All right, I see where I made mistakes.
Yeah, so yeah, it should be, but both of you did well. I think overall you had a reasonable idea of what these details are. If it was really, if you guys probably spend time, probably you guys can pick it on. That's the way I would look at it. Yeah. So I've sort of updated the grades, I suppose. I haven't curved it yet with the quiz and other things, but since there were only 2 students, I didn't bother about it too much. But both of you are doing good as such, and maybe one of these days during the weekends, I will, finalize the grades if that at all helps you guys. Yep. So yeah, general recommendation is keep doing whatever you're doing. That's good enough. Okay. So I have to post a new homework, which will be due on next Thursday. It's not yet posted, but I'll be doing that probably sometime today, by afternoon. It shouldn't take too long. It's just I missed it. And it will be due 1 week from today, so it's March 11th. So Thursday. Typically, we have the spring break, right? Next week is supposed to be this so-called scheduled spring break, which we took it earlier, right? We took it in the first week. So yeah, so that's that. And there will be another midterm 2. I don't have the dates here, so midterm 2, I don't have the dates here. No, I'll write that next time. And the final exam dates are also released. I haven't looked into it for our course. Remember that these days they announce it later in the semester, somewhere in February. So the dates are finalized. So I'll look into that and get back to you guys one of these days. Okay. And we are going slow. We lost a week almost in between because of snow. Both snow days happen to be for this course. So I'll pick up a little speed as much as possible, and we'll see how it goes. Okay. So now we want to start so-called Lagrangian mechanics, which should have been done quite early. But this is almost the 7th week running. Let's see. So let's try to motivate Lagrangian today. And the idea is, as we saw in Snell's law, it turned out that if you try to minimize something, you get Snell's law. In fact, there it was a straightforward point that you try to minimize the time taken by light to travel in a medium, and that seems to be the minimization principle. But we have Newton's law, so Newton's law is F equal to ma, right? And let's write it in a certain form. Let's see. So Newton's law would be F1 plus F2, the sum of all the forces. So recognize all the forces acting on the mass m. M is the system, and a is the motion, right? A is the acceleration, which describes the motion of the particle. So that's a simple thing we have been using. Simple or very reasonably profound, I guess, because it can explain so many things. Let's write this as dy dt times momentum, which is mass times velocity. And that's equal to, if I were to have all these forces, typically it is nice if we can write the forces in terms of energy. So the very few forces that can be written in terms of energy. What's the connection between force and energy? We know is if we do this as a differential statement, then the statement is that force is equal to negative change in energy. So this is energy. And in fact, whenever you can write this in this form, then this is called potential energy. So in that sense, it is a little more general in the sense all these forces can be thought of as a gradient of the energy. And this is also the statement that nature doesn't, or one way of looking at it is that nature doesn't really care for the forces. Nature tries to minimize the energy, and what we see as a force is just the system trying to minimize its energy. So that's a negative negative sign in front of it, the fact that it is trying to minimize it. So let's think of this as a negative gradient of energy. So there's a full F net there, and the idea is that can you think of it as a negative gradient of something. So that's how one can look at it. And we would like to think of it as, is there a functional? So the question is, like Snell's law, turned out to be a minimization statement of some quantity. So is there something that can be minimized, or let me state it as, is there a functional whose minimization or extremization leads to Newton's laws in general? Let me not say it in. Like, that means to say that is there something like energy, like this seems to suggest that energy in this spirit is more fundamental, right? If you say Snell's law is not fundamental, it's a Fermat's theorem that is fundamental. Again, a point of view there. And can we do that? And again, all this will be very specific to conservative forces. So whenever there is dissipation, we will have to give up. There is no way of writing any minimization principle whenever there is dissipation. So that will be our limited view here. So let's, so the idea is, let's say there is a functional, and what is this going to be? So this is looking forward. It is going to depend on the path of the particle, because Newton's law talks about the path of the particle itself, right? So let me stick to one dimension for a moment. I'll come back to three dimensions. I'll almost always stick to three dimensions because that's what we work in. And this is x as a function of time. So this is x. When I say x, x is a function of time. But when we notice that when we think of the functional, we don't write the t dependence in there, right? Because it's a dummy variable. So, so the w will be the functional of the path of the particle. And we are asking, is there a functional? So this is going to be your the actual statement, but we are not sure what it is, right? We would like to figure this out. And let's for now call it L. L will stand for Lagrangian. And this is x as a function of time. Since it can depend on derivative also, it can depend on the velocity also, dt of x of t. So this whole thing is nothing but velocity. Very soon I'll start writing simply velocity, but the notation will be that it is x dot time. But I'll start writing velocity, and it can depend on t also. In general, it can depend on higher derivatives also, but let's stick to that because most of the time we consider second order differential equation position and velocity seems to convey sufficient information. So with this perspective, let's try to see if there is any minimization principle we can get. And if we do this, it is based on our functional derivative information. If we try to minimize this with respect to x, so we can ask what will this be equal to? Minimize what is this? Functional derivative of x with respect to x as a function of time. We can go through the whole process, but this will come out to be so this will come out to be minus d by dt partial derivative of L with respect to velocity. So I'm just writing the statement here, and plus so this will be partial derivative of no, minus the partial, no, actually plus the partial derivative of x with respect to L. Okay, that's what. And again, we are trying to say plus, we are assuming, so this, there's an assumption that there is no variation in the boundary. No variation at boundaries. At boundaries means at T1 and T2. Actually, let me change this. Why like minus infinity, right? So let's take this from initial time T1 to T2. So the system evolves from a certain amount T1 to certain time T2, and that's our variational principle. And at the boundaries means at the boundaries T1 and T2. And this is just based on whatever we did since we spent some time on functional derivative. I can directly write that. Any questions here at this stage?
Could you lower the camera a little bit?
Oh, you should have asked that before, long time back. Sorry about that. Did you follow everything that I was saying?
Yes, thank you.
I was saying that the proposal is to write a functional of this form, and the functional derivative, if it is a minimization statement, then we have to set this equal to 0, right? So the functional derivative is this, and if this is minimized, so this will be called so the minimization principle, right? When you set the derivative to be equal to 0. In this case, it's often called the action principle, or actually, it's called the stationary action principle. Stationary action principle. Okay. And that says that you set this equal to 0. Okay. And that implies immediately that dy dt of the total time derivative of the Lagrangian with respect to the velocity will be equal to the partial derivative of the Lagrangian with respect to the position variable. Right? Okay. So let's see. Typically, the idea would be that often the idea is that if we are given the Lagrangian, we should be able to get these equations of motions, right? That's what is good. But in practice, what typically happens is that you know the equations of motion for many reasons. You already know equations of motions, and you're looking for the Lagrangian. And of course, once you get the pattern there, then you start writing the Lagrangian and getting the equations of motion. But first, in the beginning, let's try the opposite. That let's get some equations of motion, and let's see if we can get the Lagrangian for it. Okay, but in general, we will do the opposite. Within one class, actually, we'll start writing the Lagrangian, or if given a system, we should be able to write the Lagrangian and go and get the equations. But for now, let's see if we can get the Lagrangian to begin with. Let's see what the Lagrangian is built out of. Let's see. So let's learn what the Lagrangian is. And by Lagrangian, I mean this L here, right? So I should say this. So this will be called the Lagrangian. Like after Lagrange, I think within 100 years, I think 1670s, 1660s to 80s is when Newton gave his equation, but within 100 years they mastered the equation sufficiently well and started making generalizations. And by 1750s, 1780s, they had this general prescription, and they were trying to make more general statement than what Newton already did. So let's see what we can do. Let's do the simple. The simplest motion we can think of is a ball being dropped, right? A ball being dropped in uniform gravity. So this is mass m, and it's falling under uniform gravity. It's like dropping a ball on the surface of Earth, but think of it as perfectly uniform gravity, so that there is no variation with respect. The acceleration due to gravity is not changing, so Earth is flat in that sense. So we know that Newton's law for this is mass times acceleration is equal to mg, right? So you would say this is mg. And let me not cancel the equation, but m, but it of course cancels. That's a statement of inertial mass being equal to gravitational mass. Let's write this as time derivative of mass times velocity. And actually, one step more before that, let me say this is all one dimensional. So let's say this is mass times acceleration. Let me choose my z to be in the upward direction, so that's second derivative of z, and that's equal to minus mg. Right? So the minus sign is coming because of the z direction. That's in terms of derivatives. Let me write this as mass times velocity, where velocity v is equal to dz by dt, z as a function of time. And that's equal to a constant, right? That's minus mg. Let me try to, so the question is, what is the Lagrangian for this? The question is, what can we identify the Lagrangian? What is the Lagrangian? We want to have a pattern for what the Lagrangian is built out of. So we look at our equations of motion in terms of Lagrangian, which we wrote it at a very general level. And if we just look at it, that is a time derivative of something is equal to the right-hand side. So we say that, oh, this must be, let's see if we can build a Lagrangian. And let's first of all say that the Lagrangian is dependent on, let's say the Lagrangian now depends on, it can depend on x, right? It can depend on velocity v, and it could also depend on t. For some time, we'll not have time dependence too much, but we will later on talk about what the time dependence is. Okay, so in this case, now we can just comparing these two equations, right? So we just now wrote the Lagrangian equation for the Lagrangian. So it seems like maybe we can recognize, maybe, right? We want to think of a function L whose partial derivative with v is equal to mass times velocity. And the partial derivative of the Lagrangian with respect to x is equal to minus mg. That's what seems to be the suggestion. And if we have a partial derivative, we can make some conclusions about the L itself to a certain extent. So integrate this equation, and this seems to suggest that L will be equal to, if I integrate this v dv, right? So that's half mv squared. But when I'm integrating with velocity, this is a partial derivative. So I can only say that there's a constant c1 with respect to velocity. So this can depend on x, x and t in principle. Right, so that's the best we can say from this. And what can we say from here? Partial derivative with respect, oh, this should be z, right? Somewhere I screwed up here. So I was having my notation as z, so this should be z. And velocity is dz by dt, so this is z. There are not too many changes. Okay. So that says that the Lagrangian then has to be, this time I integrated with z, so that's minus mgz. And this time there can be a constant which is constant with respect to z. That means it can depend on v, right? So this is z, and this can c2 now, which can depend on velocity, and of course it can depend on time also. Okay. Together, we seem to have a relation. We can guess that what could it be if what if I choose C1 to be this and C2 to be half mv squared? It seems that the Lagrangian is equal to half mv squared minus mgz, right? Plus some constant, right? At least it does the job. It could have something else, right? Let me call that L prime. So I mean, it's already clear that this is not unique, right? If not anything, I can apply multiply a constant there, and that will be true. Whenever we are working with the Lagrangian, it's not going to be unique. There will be situations where, if not anything, you can apply always add or subtract a constant. But not only that, we will see that there is a whole generic functional you can add on to it and still not disturb the equations of motion. Right? So that will be a very generic phenomenon. There is a lot of power in that also. If whenever there is a observation you make, then you see what are the implications of that, and we will see there are some symmetry statements that you can conclude from them. But within this scenario, within the simple example, what we can claim is now let's see if we can actually check that this is actually true or not. Well, let's see. This is what we said, right? So let's immediately do the derivative and see. Right now that we have put it all together, so we have dl by dv is equal to m times v, right? That's normal differentiation here, and dl by dx is equal to minus mg. And we have to further do d by dt, right? That's also important. So d by dt of mv is equal to minus mg. Of course, that works, and it doesn't even matter if there was a time dependence in here, right? So this could have been anything depending on time. And later we will see that it can be more than that. Like we can have a more generic functional. So that's a very simple scenario where we do this, but now let us try to make this a little more generic. Again, what is this coming out to be? Identify this as kinetic energy, right? So that's your kinetic energy. And it seems like this is, if you were to have gravity, this is the potential energy, right? But not, so you're subtracting the potential energy, right? We are usually in mechanics, you add the kinetic energy and potential energy. So if this was a total energy, that would have been great, right? Or it would have worked with intuition very well that the system is trying to minimize the energy. But that's not what is happening. Notice this is kinetic energy minus the potential energy, and the point is, what is the essence of that? Why is the system trying to minimize the Lagrangian instead of the total energy, right? And that I mean, this is not a question that I have an answer for as such. So the quiz is, what is the essence, or what is the meaning of the Lagrangian? Okay, so the quiz is, what is the physical meaning of Lagrangian? And by that I mean, can you connect it with any concept you have studied in the earlier mechanics, like in introductory level physics, we learn things. And is there any quantity you can connect Lagrangian with? Is the question clear? And I would say the idea to look for is thermodynamics. Look for thermodynamics. In thermodynamics, you define these kind of Yeah, let me just leave by leaving some thermodynamics, free energy. Again, thermodynamics, you define what is called free energy. And let's say also like Lagrange transformation, Legendre transformation. So I will not go into details that the idea is that yes, there will be a minimization principle in the form of the energy, and that is what we will call the Hamiltonian. And from the Hamiltonian, you can go to the Lagrangian using the Legendre transform, and you should think of this in thermodynamics as free energy that you define in there. So there are connections in that sense. But we do see the point that, oh, okay, this is in the form of a kinetic energy minus potential energy. But that is too simple a statement, right? MA is equal to mg is too simple a statement. So let's try to do this for a more complicated system. And a complicated system will be when the potential energy is velocity, or the forces are velocity dependent. So one of the complicated forces we see around us, but at the same time, it should also be conservative, right? Remember that not many forces are conservative. So there are how many conservative forces you can think of? Maybe I've asked this before in this class. How many conservative forces you can think of?
Gravity?
Gravity, yes. Gravity is a conservative force. What else? Gravity? Yeah, electrostatics, I think that's better.
Yeah.
So gravity is, so you have potential energy is equal to G m1 m2 over r squared, r, right? And it is negative because it's attractive, right? And then there is electrostatics. And remember, force is equal to negative of gradient of u, right? Whenever it is conservative, so force comes out of that. Electrostatics, the potential energy is 1 over 4 pi epsilon naught, Q1, Q2 over R, right? And it's positive, so it's repulsive, right? What else?
Friction, I think.
Oh, friction. What is the energy associated with friction? Like, can you think of friction as a gradient of something? Which friction force are we talking about, maybe? Because we have drag forces there. And then we have the coefficient of static and coefficient of friction. And
Yeah, I was thinking of like kinetic, like the kinetic friction.
yeah, no, actually kinetic friction is not a conservative force. And it is not because typically when it is a conservative force, a good thing to not think of it is that if you go along a path, like you, let's say, gravity is a classic example, right? You start from here and you go to another galaxy, like galaxy 1, go to another galaxy 2, right? And if you were to trace back your path, you will come back and you wouldn't have spent any energy, zero energy, right? Whatever energy you lose or gain in one path, you will come back and the total energy you would consume for this is exactly zero. In fact, you don't even have to go through the same path, right? You can actually go another path, 3, and go here and come back. As far as you come back to the same point, you have to have consumed zero energy. That's a great conclusion you can make out of conservative forces, and gravity does obey this, but not every force does it. And friction is a classic example where it does not, because if you were to have an incline, when you're going down, the frictional force is acting backward, so you lose energy there, right? When it is coming back, it will switch the direction. So you still lose the energy. So by the time you have made one full circle, you only lose energy. And it seems like whenever things are velocity dependent, so this is a classic example where force is velocity dependent, right? So force is equal to some constant times minus of V. Right? That's actually not this friction, right? This is actually kinetic. These two are not connected. This is the drag force that I was keeping that has this negative kV in it. So yeah, friction is not a conservative force. So so the question is, how many forces can you think of as conservative?
All the basic forces should be conservative, right?
All basic fundamental, the four
Yeah.
forces that, but there we don't define the forces. There is only energy. So yes, so the statement is that so the weak force, right, and strong force. Yeah, that's correct. I didn't want to bring that up.
You can think of other examples like springs.
Spring is a very good example. So these two are, of course, going to be there, but this is too advanced. We have not even seen those things. So I'm not introducing spring. Right? You don't see this too much, but this is not representing any physical system. Photons, if you want, but it's very one mode of a photon satisfies that. Okay. That's force is minus kx. What else?
What about magnetostatic forces?
Yeah, very good. Magnetostatics. Yeah, very good. But the question is, what is energy then? What's the energy in magnetostatics?
You can try to like a gradient of something, but you can. It's across. What is it called? The curl of the vector field.
Magnetic field is
Yeah.
a force occur. Yeah.
The force is like the curl of a vector field.
Force is the curl of the vector field. Okay, so maybe let's go back here. So so let's talk about conservative forces a little, because friction came up. I think I should say a few things about conservative forces. Right. Conservative forces. First, remember that work done by a force is you go from path point 1 in space. Let's say this is R1 to R2, right? But to go from R1 to R2, there are many ways possible, so I have to specify a path. This itself is not well defined. I have to specify a path to go from one point to the other. And the work done by the force is given by, along the path, calculate the L dotted with the force. That's the work done. But if this is, if the work done along a circular path, arbitrary, you say path independent actually. If you go along a circular path and this is equal to 0, then that's a definition of conservative force. The work done is exactly 0. This means that if we use the Stokes theorem, then you immediately see that, oh, okay, so this would imply that I can write this on a surface, right? So this is on a curved path here like this. Whenever you have a path that can be thought of as the boundary of a surface. The surface is not unique. Whenever you have a line, the surface is not unique. It could be the plane in this board itself, but it could also come out, right? So it's not unique, but you can always think of this as some surface, and that is dA dotted with del cross of F is equal to 0. And if that is the case, you conclude that, oh, if it is conservative, so that's one statement, that it is path independent. And the second is, let's turn the visible. So second is that the curl of the force, I think that's what Harshra is trying to point out, is equal to 0. Right? And there is a third statement, right? What's the third statement you can think of? And yeah, if this is the case, if the curl of the force is 0, that also implies that the force can be written as a gradient, right? If the force is a gradient, because the curl of a curl is, sorry, two gradient operators when there is a curl because of antisymmetry, that's equal to 0 minus. So there exists a potential energy. That's what we say, right? So this is called the potential energy.
So curl of the magnetic field need not be equal to 0, right?
Yeah, that's not 0, right? Exactly. Again, if there is a conservative force, any three of these statements are true. One implies the other. It's not necessary that you begin from here and you go in this logic. You can start from any one of this and go to the other. But all three statements have to be true. And if there's a conservative force, that's a well-defined statement. Okay. And the whole of Lagrangian that we will work with, it will be true only if this is true, like all for conservative forces. Okay. If it is not conservative, then at least at some higher level it has to be conservative. We will talk about dissipation, and there was a lot of work in the 1800s basically to understand the Lagrangian for dissipative systems. D'Alembert did a lot of work there, but we will keep it minimal. But it is possible to a certain extent, surely not for friction. Like whenever we have a kinetic friction, like the friction that we talk about, static friction, kinetic friction, that's not conservative. And there is not even a hope, I think, to do that by using Lagrange. Like you will never see a Lagrangian problem with where there is kinetic friction or static friction. And that's why probably engineers never use Lagrangian, right? Because they use real life, and that's not very useful. So this is for very fundamental physics. And these are only the forces that we know conservative. So very limited region where the Lagrangian is really applicable. But we will do a certain, for example, even though I said kinetic and static, you cannot. There are systems where you can avoid friction. For example, a classic example is when you were, if you were to do this sphere rolling down the plane, right? Like when you do the sphere, if I were to do this problem at here, right here, the way you would, so let me ask the following question. I'm just trying to make a point here. So let's say this is velocity 0 in the beginning, and let me ask, what is its velocity here? And it is perfectly rolling. Perfectly rolling means V is equal to omega R. Like how much ever angular velocity it gains is exactly equal to how much linear velocity it gains. And you would do, energy is conserved, kinetic energy is half mv square plus half I omega square plus ngh, right? It's falling under gravity, is equal to constant, correct? That's what you would write down, right? And this will give you an answer, right? So the final, so this has to be the same as the earlier, so you would say, and let us say this is a perfect sphere. Let me quickly do this, okay? Is it okay if I just jump the steps? So this implies that the final can be solved. Okay. Now here is my argument. Is that clear, Ken? Are you there with me?
Yes.
Okay. So here is my argument. If I have to roll this, I need friction, correct? Otherwise it's not going to roll. And if there is friction, where is the friction energy? So what about the energy you lose in friction, right? So what happened to this equation? Like, is this correct? Is this an approximate relation that we derived? Right? This is actually true, correct? Like, there's nothing, we're not actually approximating anything there. So what happened to friction? What, are we not losing energy in friction here? Right? Is the question clear?
So I think it's because the surfaces never actually move against each other. They're always static.
Yes, so there are various arguments that you can give. One of the arguments is exactly what Harsha, you're pointing out, is that this velocity profile of the perfectly rolling sphere can be thought of as this is velocity v. At the highest point, its velocity is because it's going in a circle, right? It adds up, and it is 2 times v. It is v plus omega r. And at the very bottom point, actually, it is trying to go in the backward direction. It is at rest. Its velocity profile is something like this. And right at the bottom, its velocity is 0. And you say that, oh, that's 0. So if there is no relative velocity between two surfaces, it is at rest. So friction doesn't even act on it. So in a perfect rolling, friction, that's good enough. That's a very good argument. But you can also think of it as, in case it is actually losing, what you can do is that think of what is the energy lost in linear motion. So if this was linearly sliding down, you will lose some energy. But since it is angular, it's also gaining energy. So friction assists rotational motion, and friction leads to dissipation in the linear motion. And that cancellation is very fine in this case. And that is the best argument for them. Right? But if you want to think of it as a mathematical expression, the energy lost in linear motion is exactly cancelled by the energy gained by rotational motion. So you can imagine that there are dissipation and things going on, but there is balance of that thing happening. And in magnetism also, there is a similar interplay going on. Even the best example you can say is that what's the work done, right? This is going randomly everywhere, but think of dl. So the work done dw, right? Work done is equal to dl dotted with f, right? Small at some small instant. But the force due to a magnetic field is dl dotted with q v cross b. At some point, velocity is L dotted with velocity is dl by dt crossed with b, and that is q. Okay. This will always be 0, right? There is a dl here. dt is a scalar. Change in position is what causes velocity. So there is a cross product which will be perpendicular to dl, and then you dot it with dl again. This will always be 0. So the work done by the magnetic field is 0, very similar to the what we said just now, because of it's an analogy, it is not a one-to-one correspondence there at all. But here, that doesn't mean that it doesn't have any energy. It doesn't mean that it doesn't change its energy. We will see that there will be energy associated with magnetic field. But a simple way to look at it is that it also changes momentum. So the simple scenario is that if a magnetic field will make a charge go in circles, right? Its energy doesn't change, right? Half mv square. Magnetic field doesn't change its energy if it's going in circle, but it's changing its momentum. Right? So there is a change that it is causing, and we would like to see it as can we write a Lagrangian? So remember that if it is dissipative, then Lagrangian is not very useful. Right? So, but we will write a Lagrangian for the electromagnetic force acting, or the Lorentz force acting on a charge. Okay, with that very haphazard discussion on conservative force, let me go and get back to the problem I was trying to address. By the way, any questions at this stage? Even though it was very randomly oriented at various things, what I was trying to point out is that one simple point I wanted to convey is that there are dissipative systems, and Lagrangian is mostly useful only for conservative systems, which are very few. Okay, and let's do an example. Can any questions?
No questions, thank you.
Okay, so let's do the simple example. We want to keep it constant magnetic field. Yeah, I think so. Let's say a point charge in a I think it need not be uniform in an electric and magnetic field. Maybe as we go, if necessary, I will make it uniform electric and uniform magnetic field, but I think it is more generic than that. Okay. So we know that the equation of motion for this is mass times velocity is equal to, what is the force acting on a charge? QE, right?
QE cross B.
And QV cross B. And let us, so yeah, so that's our problem. And let me see. Yeah, I don't think I want to keep, this is more general. This is very general. Yeah. Yeah, so let's have very general system. And the question is, can I get a Lagrangian for this? And the Lagrangian will be dependent on the position or as a function of time, and derivative, which I will write as velocity, right, as a function of time. This is not a new variable. This is just a notation. Velocity is r dot, if you want, r d r by dt. It is just a notation. It is not an independent variable. And there is time also. It will turn out that there is no explicit time dependence. We very rarely work with explicit time dependence, but still, we will talk about what is the relevance of that in the next class when we make this more general, when we take away the boundary variations completely altogether. We will have a general stationary action principle coming in. As of now, we are just doing a warm up. Okay, so that's the question. Right? What is yeah. Okay. Any questions, sir? That's it. Yeah. Any concerns? I'm asking myself actually. I'm worried if this has to be uniform or not. Okay. So that's our condition, but we're going to do something more than this. Remember that electric and magnetic field can be switched to potentials, right? Remember, you have electric field. Whenever we do electrodynamics, magnetic field can be written in terms of respective potential, and this is del crossed with A. Right? So there is a vector potential. It always gives you the magnetic field. And what is the electric field in that spirit? What is the potential that gives you the electric field? And that is negative gradient of the voltage, right? So this is the electric potential, which we will call phi. This is in introductory physics, we use it as electric potential V usually in standard textbooks, or the more recent textbooks we use V here. But here we will call it the scalar potential, and this is the vector potential. Is that familiar ideas? Ken?
Yes, yeah, for sure.
Right. Harsha,
Yeah.
so what am I missing then? I say this is not correct.
Oh, yeah, I remember. Isn't E also depends on A?
Yeah, that's right. Because del cross E, remember in Maxwell's equation, del cross E, if I do using this, is minus of del cross del of phi, right? This is 0. But del cross E is not equal to 0. Del cross E is equal to 0 according to this, but in Maxwell's equation, del cross E is equal to minus Faraday's law, right? Yeah, that doesn't seem to be giving you that relation. So because of that reason, there has to be a new term here, A by dt. In that, can I use this? Ken? Sure. Ken, are you struggling with the internet? Yes.
Just a little. I haven't really refreshed on electromagnetism.
Oh no, I was saying internet is okay, right?
Oh yeah, for sure.
Internet connection is okay. Yeah, I'm wondering that you had trouble with that connection. Yeah, that's okay. Yeah. So how about this? So yeah. Instead of might not be this detail, but let's say instead of claiming that yeah you should have seen this before, I say that let's write electric field and magnetic field in this form. Right? So I can always construct my electric and magnetic field in this form, where phi will be called the scalar potential. If you're already experienced with this, then you can have an intuitive feel for this. But otherwise, these are just new potential. So let's think of the electric field in terms of electric potential. Think of potential energy. If it is electrostatics, this is the term that comes in. If it is magnetostatics, it is just this A, and this comes only when you go beyond statics. You have to do dynamics to get the change in the vector potential with time. Okay. As of now, they are just new functions, if you want. So if that is the case, I get my equation to be time derivative of mass times velocity is equal to replace your electric and magnetic field, correct? So this is negative gradient of q times phi, q times phi, and nothing else. That is this term minus partial derivative of q times a, and put this in here. So that's plus q times v crossed with curl of a. And I did not restrict myself to uniform electric and magnetic field. This is very general. These are all position and time dependent quantities, right? Phi and A are position and time dependent. So if they're uniform, then there are simplicities to it, but I want to keep it very general. This is all of electrodynamics if you want, as of this. Every electromagnetism problem can be worked out, is applicable for this equation, this state. Okay, so if that's the case, let's you go further. And remember, we are identifying the Lagrangian. So we want to write this as a time derivative of a gradient, right? Time derivative of, let's say, mass times velocity of momentum has to be equal to some gradient of something. So the idea is to write this whole thing as a gradient or a time derivative. Okay? So let's expand this as a gradient there. So let me try to expand that. And this is a time derivative, so I'll try to bring this to the left. But it's not total time derivative. We differentiate between total time derivative and partial time derivative. Mass times velocity. And this is plus partial derivative of q times a. Already see, I tried to sort of mention that magnetism throws up as momentum. Seems to have that connection there, but this is partial derivative and total derivative, not yet ready to be identified as momentum. And this is surely electrostatics we already. That is a electrostatic energy in there. That's Q times phi. But this is not at all ready then, right? So let's see what this is. First, let's expand this out. Remember, these are all position types are dependent, but velocity is the property of a particle. That's not a gradient. That doesn't depend on a variable of position, right? Velocity is the property of a particle, so at the position of a particle. This can actually go in and out, but as of now, let me keep it as it is. This is the curl product, so let's do this carefully. So first vector will have the gradient as a free operator. That's Q times V, and then gradient has to still act on the magnet on the vector potential. Right, so that's the free vector here, and these two are dotted. That means the vector product is applicable on B and A, and the gradient acts on the vector A. Right, I don't want to take this in. I can't take that because this doesn't depend on the gradient. Okay, but as of now, in general, that is not applicable. But I have to use that assumption that velocity is not position dependent. I can take that inside. Okay, and there is a new another term that is in the direction of A, and these two are dotted. That's Q times V dotted the gradient. So this is easy because gradient still is acting on A. So this is a directional derivative, right?
Like the level of V dot A, because V is anyway.
Yes. That's what I'm going to do in a second. Yeah. But I wanted to clarify that in that I am assuming that velocity is position. The variable. I want to clarify that. That's all. In general, that is not. Yeah, but I will take that in. Good. And when I take that in, that's nice because then the gradient, that's a gradient operation. And this is not a gradient operation, that is a directional derivative. It's the derivative in the direction of velocity. It's not really a gradient. So, since that doesn't fit into the gradient, I'll take it to the left hand side. See if I can recognize something wrong. Left hand side. So let's the following. This is a plus and this is acting on A. This is also having an A. So let me see if I can write this as plus B after that. So that sticks together. And the right hand side, this is now gradient, right? So this is negative gradient of Q times phi and negative actually. So that raises a question. Why is that negative? Q times V with A. Okay. So we do have, so this is the magnetic energy if you want. Magnetic energy is given in terms of A. Right? But at the cost of a lot more terms, right? What is this? First, let's concentrate on this. Where else do you see this operation? What is this equal to? Let's start with, what is this equal to? What is this quantity in the parenthesis as an operator? Like, think of your calculus. What is this operator equal to? You see it in maybe partial derivative.
Looks like the flow.
Flow, very good. Fluid dynamics, right? Flow, right? Flow. Without the V, why do you say without the V? It is necessary. Right? With the V, it is exactly like a flow. In fluid dynamics, you see that. But V is important, right? I don't know why you would say without the V.
The J, right? Like current density.
Yeah.
Isn't it just go by 2T plus del of J?
Oh, that is the flux. No. That is slightly different. Yeah, that is a flux.
Okay.
Yeah, that's the definition of a flux. Yeah, I see. So there what you're saying is that d rho by d plus del dotted. That's on the other
right,
side.
right.
Del dotted with J.
No. Okay, so J actually has velocity involved.
Yeah, but that is inside.
Yes.
But that's different.
Yes, it's kind of the same thing. Okay, no. It's inside the del.
Yeah.
No, not inside the del. Okay, I understand.
Yeah, but that's like, this is a conservation of mass statement. Yeah, but fluid dynamics has that also. Agree, you want that. But this is slightly different. This is more like if you have a function f, let's say f is a function of x, which is also a function of time, and it has a time t also, right? And if I were to ask, what's the difference between total time derivative and a normal time derivative? Like, what's the time derivative in this? You would say that when I say the total time derivative, it has to act on every time. This is called the implicit time dependence, and this is called the explicit time dependence, right? So when I say total time derivative, it has to act on both, and the partial derivative acts only on this. Okay, so that's the difference. So this is equal to partial derivative of f with time. By that I mean it hits only on this time. But we know that it can hit on this also in the total sense. But how do I hit that? I can use a chain rule. So I will do chain rule is plus df by dx and then dx by dt. Right? That's a standard what do you call it? Partial derivative course, right? But if it is only dependent on time, if there is only one variable, it doesn't matter whether it's total derivative or partial derivative. If there is only one variable things depend on, then it's dx by dt. Total time derivative is the same as partial derivative. Partial derivative concepts are applicable for more than one variable. And this is in 3 dimensions. This generalizes to v dotted with the gradient, right? And if it's a vector, if f is a vector, then it's a general vector relation. Is that okay? Ken, any questions?
No, thank you.
Yeah. Okay. So with that idea, then we learn that this is equal to total time derivative. That's very nice because then I have what we will call the momentum. That's equal to minus gradient of q times phi. But before we identify the Lagrange minimum also, but let's slow down a minute. I think this is useful. Okay. So in electrodynamics, so there are 2 things that comes out of this, right? Apparently, momentum is not mv anymore. You always think momentum as mass times velocity. No, that's not mass times velocity. Sometimes it is more than that. It could be position dependent quantity. A is typically a position dependent quantity. And this is generally called canonical momentum. It's a classical mechanics idea. In fact, whatever comes in the term total, if you can ever write an equation of motion as total time derivative of something is the gradient of something, whatever is the total time derivative will be called the momentum, canonical momentum, whatever that quantity is. And that's because immediately this is your, if there is a Lagrangian, this is velocity. Now it's a gradient of v, right? So what I mean by partial derivative of the velocity is that that's a gradient with respect to the velocity vector. And there is an energy, right? So there's an energy which has an electrostatic part to it. And there is an opposite sign quantity. And there is a magnetostatic or magnetic quantity. So in that sense, so when we earlier said that, oh, there's a balance, yeah, there is. It seems like the magnetic field never does work on a charge, but there is still energy associated with it, but there's also momentum associated with it. So magnetism works both on momentum and energy. So that brings in a lot of richness in there. But we will proceed and get the Lagrangian next time. In your homework problem, actually, you do this whole thing. I remember usually I give the homework problem, you do the whole thing for relativistic particle. Like that's almost everything goes through, except that to begin with, this is not MV then. But the ideas you will use is exactly the same. And we will actually start from this one. So I'll give you more hints next time. So you're not yet ready to work on the problem. But let me start by discussing one point here. Why is this negative? What's the relevance of that? Why is the magnetic energy negative? So remember, positive, if gravity has potential energy as negative. What does that mean? Two masses attract. And charge, electrostatic energy is positive. That means two positive charges repel. And here we are having in magnetism, apparently, we're getting a negative sign. That means magnetism is attractive in some sense. In what sense is magnetism attractive?
Like if you have two wires, the same current.
That's exactly correct. Yeah, so this is the statement that like currents will attract, like charges repel, like currents will attract, and that's the negative sign that is fundamental. That's the meaning of that negative sign. So you have two current carrying wires, they will actually attract, and two wires with opposite currents will actually repel. So this is attractive and repulsive. And they will repel like this. Yeah, whatever that actual signs. Okay, so we'll come back and do the Lagrangian next time, and we will go from there. And then we will, once we have a reasonable idea of what this Lagrangian is, then we will do some problems on given the system, how do you write the Lagrangian itself, and proceed from there. That is all. Yeah, thanks. Any questions, comments?
No, thank you.
Okay, good. Yeah, okay. Yeah, yeah. Ken, shall I stop?
Yeah, sorry, I was just finishing writing down some stuff.
sure,
No, I
sure.
got it all. I got it all down. Thank you. Thank you so much.
Wait, yeah. Yeah, maybe it was all happened here and there, but I was trying to. And next time probably it will be more systematic. Okay. Have you seen Lagrangian before? Related to this?
Lagrangian, yeah, I mean, I've messed with it in math methods for sure.
Oh, sure. Okay, good. Okay.
Yeah, and then I think a little bit in E&M.
Yeah.
But
E&M, this is a very complicated example. I just started with it so that that's a most sophisticated one. We'll do simpler examples. Okay?
Okay, sounds good. Thank you so much.
Yeah.
Okay, goodbye.
Bye-bye.